All right, guys, so let's get into a new type of function here. This is going to be periodic functions, which are also known as repeating functions. And this is something totally new. We have not seen functions before that like kind of do a little pattern and then repeat itself. You know, if you think about linear functions, they just go on forever. Quadratic functions, square root functions. And any type of function we've kind of done just either keeps going or, you know, it doesn't have like a repeating pattern to it. So I want to take a look at this example. This is like a situation everyone can hopefully envision themselves in and just see how it works and then see if we can kind of analyze it a little bit more. All right, so let's envision we're sitting on a Ferris wheel. Okay, so a big Ferris wheel going all the way around. Let's say this one takes 20 seconds to do a full revolution. We're going to be starting at the bottom, so we're starting out right down here. Okay, so there's you all excited getting on. And at the bottom, you are 3 feet off the ground. Okay, so when time, I'm going to fill this table in. At time 0, when you first sit on there, you are 3 feet off the ground. Okay. All right, then you're going to start making your way around. We're going to be going this way. Okay, as the Ferris wheel goes, and it's going to take 20 seconds to go all the way around. So at 20 seconds, you're going to end up right back down where you were before. You're going to be at the bottom again. So at 20 seconds, you will be 3 feet high. Okay, so let's see what happens as you move around. Okay, if we think about as you're going around, so 20 seconds is a full revolution. So at 10 seconds, you would be up at the top here, right? At 10 seconds, you would do half of the circle. So how high would you be then? Okay, so it's telling us here, if we think about the diameter of the wheel is 35 feet. Okay, so from here all the way to the top, there to there's 35 feet. And then also the when you're at the bottom, you are 3 feet off the ground. So this little distance is 3. Okay, so when you're at the very top, right? So if you think about this, as you go around this thing, you know, at 5 seconds you're going to be here. 10 seconds you'll be up here, 15 seconds you'll be over here, and then 20 seconds you'll be back down at the bottom, okay, doing a full circle. So it's kind of splitting it up into 4 intervals, right? The 20 seconds, 4 intervals will be 5 seconds each. So let's think about when you're at the very top, right? This is going to be where you'll be at 10 seconds. Okay, you are the 3 feet off the ground, okay, right here, plus the 35 feet of the wheel. So you're going to be actually 38 feet off the ground at your highest point. Okay, when you're at 5 seconds, okay, 5 seconds, you will be, we said over here, okay, so that's going to be your total height would be the 3 feet plus half of the 35. Okay, so half of 35 is 17.5. So 3 plus the 17.5 is going to put you at 20.5 for a height. Okay, then when we get over to 15 seconds over here, okay, you would be back down to that same height that you were at 5 seconds. Okay, and then again at 20 seconds you're back at the bottom. And then here's the thing where this starts to repeat. Okay, at 25 seconds, you'll be back up here again. Okay, so you'll be at a height of 20.5. And then at 30 seconds, you'll be back up at the top again, 38 feet high. Okay, so let's kind of walk through and make sure we're comfortable with everything. So take a look at what we got. So the table, starting out, okay, right here, we are 3 feet off the ground. Okay, 5 seconds go by. You're over here, 20.5 feet, right? Half of the diameter, half of the diameter of the wheel plus the 3. Okay, at 10 seconds, you're at the highest point, which is 38 feet. And then you start to come down on the other side. Okay, 5 more seconds go by. So at 15 seconds, you're back down to the 20.5. And then at the full 20 seconds, it did its full revolution. You're back at the bottom at 3 feet. And then it just starts to repeat itself again and again. And this would keep going. We could do this over and over, however many times you're lucky enough to get to ride this thing. Okay, so let's take a look at what those points look like, you know, if we were to plot them. And let's see what was going on there. Here, the x value was the time in seconds, so it doesn't really apply to being an angle in a triangle. Okay, so radians are going to be the... Okay, so before we get into some more details, let's go back to basics and just think about what would the graph of y equals sine of x look like, okay, or the graph of y equals cosine of x. So what I want to do, I want to take you guys back to the to just a unit circle, and really we're not going to have to worry about all the coordinates around. I just kind of want to focus on 4 main kind of stops along the way. Okay, so let's think about over here, the coordinates on the unit circle, the x would be 1, the y would be 0. Up top here, we would have an x value of 0, a y value of 1. On the left over here, the x is -1 and the y is 0. And then down on the bottom here, we are at 0, -1. Okay, and let's just think about those angles, okay, because the angles that we're talking about are going to be the x value of the graph. So this was at 0 degrees. Okay, this over here was the 90 degrees. We're actually going to be using radians for these graphs though. So the radian equivalent is pi over 2. Remember over here, 180 degrees, we're going to be using pi as the radian value, okay? And then down here was a 270 degree angle, which is 3 pi over 2. Okay, now when we're doing graphs and applications of these things, we don't really use degrees. Degrees are kind of more limited to when you know you're talking about a triangle or measuring an angle in a triangle or something. And a lot of these problems, you know, like the Ferris wheel, the x value, if we're going to stick with, I will mention degrees a little bit just to kind of get us familiar with things, but kind of get used to using radians for all these graphs. Okay, so let's get these set up. Let's start with the sine graph first. So let's just think about, we're going to make a graph here. Okay, and what we're going to do, like I said, we're going to just use these 4 points on the circle as kind of like our little x values, and we're just going to focus on those. Okay, so what I want to do, we're going to start at 0, and in this first little interval, I want to be pi over 2. Okay, and then pi for x, then 3 pi over 2, and then finally 2 pi. Okay, so those are going to be my x values. And what I'm going to be doing is just graphing the y value that goes along with it. Okay, so what I mean by that, when we think of sine, okay, sine are all of these y coordinates. Okay, remember how the sine value is the y coordinate of the unit circle. So what I want to think about is when the angle is 0, okay, what is the sine of 0 basically? So the sine of 0 degrees is the y coordinate right there. Okay, so the sine of 0 is 0. So my y-intercept is going to be 0, 0. Okay, when I get to pi over 2, the sine of pi over 2 is this y coordinate. So I'm gonna plot that pi over 2. The y coordinate is 1. That's the sine of pi over 2. Okay, when we're at an angle of pi, the sine of pi is back down to 0. Okay. When we get to 3 pi over 2, the sine of that is -1. Let's see, how can I do this? Let me move that 3 pi over 2 so we can write that on there. Okay, because the point would be down here, and that's an x value of 3 pi over 2. Okay, and then when we get back to 2 pi, 2 pi is a full circle, the sign back there is 1. And then what's going to end up happening is this thing will just repeat itself again and again. But the actual shape of the graph of the sine curve is going to do something like this. Okay, I'm going to put the little arrow because it's going to keep going. What ends up happening, this point right here is exactly the same as this point, like when it starts over. So it would continue and it would just do that same pattern forever. Okay, it would go infinitely. It just continues and continues forever and ever. Okay, so that's a basic sketch of a sine curve. Let's take a look at the cosine curve so we can kind of see the difference. You know, we need something to compare it to really see what it's doing for us. So a cosine curve, okay, we're going to do the same thing. We're going to use the same x values here. Pi over 2, pi, 3 pi over 2, and then 2 pi. But this time when we do it, we're going to be focusing on the x coordinates because those are the ones that represent the cosine of those angles, right? Cosine is always the x coordinate on a unit circle. Okay, so let's get these set up. I know it's going to go from 1 to -1. That's kind of the basic of the parent function. That's going to always be the range, right? The y values always kind of lie between there. So if we think about when x is 0, okay, when I'm at an angle of 0, the cosine there is 1. So this is going to have a y-intercept of 1. When the angle is pi over 2, or 90 degrees, the cosine is 0. So I'm plotting the cosine at 0. Okay, when we're at pi, the cosine of pi is -1. The cosine of 3 pi over 2 is back to 0. And then when we get back to 2 pi, the cosine is back to 1, and it's going to start to repeat itself. So we end up with this kind of thing. Now, don't draw it like a parabola or an absolute value. Both of the endpoints actually need to go back down because, again, this thing's going to repeat. This point here and that point right there are kind of the same, and it's going to repeat that pattern again, okay, over and over and over, and we'll just keep going and going and going. Okay, so those are the basic parent functions. Make sure we know those. And again, they all just go back to the coordinates at the 4 special angles on the unit circle. Okay, knowing those basic parent functions, we're going to be able to then apply transformations, set up applications, and kind of analyze all of this stuff. So these are really, really important to have these down. All right, so let's take a look. We're jumping into the old book here. This is, I believe, the Algebra 2 book. So basically, again, this is just showing a definition. Okay, so a periodic function, as we said, it's a function that repeats its values in a regular interval called a period. Okay, so the graph that we see here on the top, okay, that one right there, it shows a periodic function. We can kind of see it's doing a repeated pattern. Let's say we wanted to start analyzing here. It kind of does this down, then back up. That would be like considered one cycle. And then it starts to do it again and again and again. Okay, the graph on the bottom, you know, it definitely looks to have some sort of pattern going on, but it's not necessarily repeating its entire shape. Like it's not doing a set. What's the word I'm looking for? It's not doing like a set pattern and then repeating itself. Okay, so let's look at one where we can kind of talk about some specifics on here. If you take a look, some key terms, and these are important over here. So these, we definitely know what these mean. So a period is going to be the horizontal distance required to complete one cycle. Okay, so think of it like a time period. It's usually a measurement of time. The amplitude of a function, we're going to see, is going to be half the difference between the minimum and maximum values of the range. So it's kind of measuring, I like to sometimes think of that as the height from the center. Okay, and we'll see some examples, but amplitude is going to measure more how tall it is. It has to deal with the y values, but it's not the total height, I'm sorry. It's going to be like half the height, or the half from what we call the midline, which is our next term here. The midline is a horizontal axis used as the reference line about which the graph oscillates. Oscillates means going up and down and up and down. Okay, so let's take a look at an example and then kind of do some on our own. So you see this one here, they graphed the function. Okay, here's the function, periodic, kind of doing this little repeat cycle over and over and over. Okay, and one good way to kind of see some of this stuff is to do what they did here, where they drew a box around one full revolution, or one cycle, I should say. So you can see that does a complete cycle. If we started here, it goes up, comes back down through 0 to its minimum, and comes back up. That covered one complete cycle, and then it starts to repeat itself. Okay, so this one, it's basically telling us the period, okay, is the horizontal distance. How long did it take to do one cycle? So you're kind of measuring the width of one cycle would be 2 units. So this one would have a period of 2 units. Okay, now if we take a look at the max and minimum of this graph, the maximum up here, the highest it ever gets is 6. And the lowest its y value ever gets here is 2. Okay, so that's telling us the amplitude, okay, is going to be half of that difference. Okay, this graph has a total height from 2 to 6. The total height is 4 units, but half of that is what the amplitude is, which is 2. Okay, and then the midline we see, the midline is going to be kind of the midpoint, okay, midline. It's going to be this line right here. It's the exact center of the 6 and the 2. You can find it by finding the average, okay, 6 plus 2 is 8. Cut that in half and you will get y equals 4 as the midline. Okay, so let's do one on our own, kind of see it together. Okay, here's a graph, here's an example. Okay, we have this function going on here. I'm going to highlight one full cycle for us just so we can see it. And you could start at different places. I'm actually going to start at the y-intercept and do a complete cycle. So a complete cycle is down to the minimum and then back up all the way to there. Okay, that's where it's going to start to repeat itself. Okay, you notice the pattern. If we drew the box around there, it would look just like that, the rectangle. That encloses one complete cycle, right? Okay, so we drew a rectangle around there. How wide is the rectangle that we drew? Okay, it looks like, and that's why I started with the y-intercept, so we kind of have a starting point. If it's starting here and goes all the way to 8, okay, its width is 8 units. That is the period of the graph. Okay, it takes 8 units, you know, maybe that's 8 seconds or 8 minutes or whatever, probably a time measurement. That's the length, okay? Oh, in this case, it's the width of the rectangle, but it's the length of time in the x unit to do one full cycle. Okay, how high is this rectangle? So in this case, we can just count it out from the bottom to the top. 1, 2, 3, 4, 5, 6. Okay, the height of the rectangle is 6. Okay, that's the difference in the min and the maximum, but the amplitude measures half of that. Okay, and once we get that midline, I'm going to show you a different way to think of the amplitude. The amplitude is actually 3. Okay, it is not 6. That's one confusing thing. It's not the entire height. But if we think about what would be the midline here, okay, the midline, if our minimum is -4 and the maximum is 2, okay, what's right in between -4 and 2? We find the average, add them up and divide by 2, just like finding a midpoint in geometry. -4 plus 2 is -2 divided by 2. -1, y equals -1, which would go right through here. Okay, that's the midline. Okay, that's like just the straight midpoint of the min and max. It's the midline, and hopefully that helps see that the amplitude, remember we said the amplitude is 3, right? So the amplitude measures the height from the midline, okay? From the midline, oops, let's do a yellow. From the midline to the top is 3 units, okay? Also from the midline to the bottom is 3 units, okay? So the amplitude is 3 units, even though the total height is 6. Okay, so let's take a look from our warm-up and see if we can now answer. Okay, so here's a graph showing those points, and we'll talk about the period, the amplitude, and the midline as we go a little bit. But let's just kind of think about it again. So here's the x-axis is the time in seconds. Okay, and the y variable is your height in feet. Okay, so when you first start out, there's the 3 feet. The 3 feet height, and then we have 5 seconds. We said we were 20.5. Let's see if I can. Then we would have at 10 seconds. That's when you're at your highest, which we said was 38, I think it was. Okay. At 15 seconds, we were back down to the 20.5 height, and then at 20 seconds, we were back down to the bottom at 3, and then it just kind of repeats itself over and over. So you get this wave kind of graph. Okay, and we're going to see in a second here, this is going to be a trig function graph. It can either be a sine graph or a cosine graph, or it could actually be written as either one. With a little bit of manipulation, you could use either one. Okay, but let's take a look at what some of these terms mean and see how it all fits together. The period, amplitude, and midline. Okay, so if we take a look here, this was the function. Let's try and highlight one complete cycle. Remember, this was the Ferris wheel. So if you're going around the Ferris wheel, you start out at the bottom, right? They told us it took 20 seconds, so we know get up to the top at 10 seconds, start coming back down, and then right there is where it's going to start to repeat again. You would go around the wheel again. Okay, so for this one, if you want to do where you draw the rectangle method, that might be helpful. It would go from here to here. Okay, something like that. And that might just help kind of see what's going on again. So let's think about, so period again is going to be the time to complete a full cycle. In this case, we can see that is 20 seconds. That is the width of the rectangle we drew. Okay, every 20 seconds, things start to repeat. Okay, let's actually find the midline before we find the amplitude. So the midline, if you remember, our maximum is up at 38, and our minimum was 3. That was just like the height of the Ferris wheel and all that stuff. So the midline is the average of those two. Okay, so 38 plus 3 over 2 would be 41 over 2, which is 20.5. Okay, 20.5 is the midline. And that's actually the point that we were at when we were on the sides of the Ferris wheel. Remember, we were at the 20.5? Okay, that's always going to be the case. That's going to be like your center. Like you're going to always go through that on your graph on the way up, and then back on the way down. You're going to go through there, and it's going to go at the nice time intervals that we'll see how to get those set up in a second here. Okay, but that's the midline. That's kind of like the middle. Now the amplitude, 2 ways to do it. You can either do max minus min over 2. Okay, 35 over 2, which is 17.5. That's kind of one way. It's probably the book formula you'll see. The other way is just to measure or calculate from the midline. That's why I wanted to find the midline first. From that 20.5, how much is it to the top? Okay, so do 38 minus 20.5, or that same distance is from the midline to the bottom. From 20.5 down to 3, you can see it's 17.5 each way, and that ends up being what we call the amplitude of these graphs. Okay, that's the amplitude. All right, so hopefully that helps. That is some of the key features of these graphs. All right, so let's take a look at how to graph these trig functions when it's not just the parent function. And we'll just start with the basic case of just the amplitude change. So what I'm going to do, what I'm going to suggest you guys do, is always graph the parent function. Let me use a better color here. Always graph the basic parent function first that does not have any transformations on it. Okay, and what I mean by that, the basic parent function here is just y equals sine of x. Okay, these, since they're new and they're kind of a little more complicated, we want to think about what does the parent function look like, and then we'll think about, all right, what impact is that 3 having? Okay, so if we think about, again, just the basic setup for the parent function, think about the 4 points along the circle. Since this is a sine graph, we're going to be plotting the y coordinates. Okay, so let me just write these out one more time here. -1, 0, and 0, -1. Okay, let's go ahead and set up the scale. Okay, you're always going to do 4 little intervals because we always have 4 special points. It'll be pi over 2, pi, 3 pi over 2, and 2 pi, because those are always like the special, kind of quadrantal angles as we call them. And if we think about this case, since we're graphing a sine graph, again, we're going to be worried about these y coordinates as we go around. Okay, if it was a cosine graph, then I would be looking at the x coordinates. Okay, so the parent function first. I'm going to do the parent function first. Parent function starting out at 0, 0. Okay, by the time we get up to pi over 2, the value is 1. When we get over to pi, the y-coordinate is 0. At 3 pi over 2, it's down to -1. And then back to 2 pi is starting over. Okay, and do this one light, or use like a pencil and do it real lightly, because this is just going to be like our, kind of like a guide. This is not our final answer. This is just y equals sine of x. Okay, the one we really need though is y equals 3 sine of x. Okay, so if we think about all the transformations, all the work we've done, when you multiply by something on the outside, that's going to represent a vertical stretch. So what I'm going to do is use these points here, okay, and we have, what, 5 points plotted. They're each going to get their y values multiplied by 3 because we have a vertical stretch. So let's think about what that does. This first point right here, its y value was 0. It's going to stay at 0. Okay, this point right here, y value was 1. It's now going to be multiplied by 3, and it's going to end up at 3. Okay, this point had a y value of 0, so it's going to stay at 0. Right? When you times 0 by 3, it's still 0. The next point here had a -1 y value. If I multiply it by 3, it's going to be moved down to -3. And then this one's back to 0, or stays at 0, I should say. So our final answer, it still has that same shape. It's still a wave graph, sine graph. It's just been, you see how it's vertically stretched from the red graph? That's what the amplitude change is doing. Okay, this graph has an amplitude of 3. Okay, because it's midline. Okay, if you can see the max and minimum were 3 and -3, the midline of that is actually right here. Okay, this is the midline. The midline is at y equals 0. And the only thing that's going to change that, we'll see, is if there's a vertical shift. If there's a plus or minus something out here, it would shift that midline up or down. Okay, now the other key features that we talked about, the midline we said again was y equals 0. The period, okay, how long did this thing take to do a full cycle? It did its full cycle, if you think about one full circle around, is 2 pi. Okay, 360 degrees, 2 pi. That's going to be the period. We'll see some changes later, but for now, this one didn't have any. And then our final amplitude again. The amplitude is measuring from that midline, okay, from the